Thank you, Scott. And what you didn't tell them what my last name means. So my last name is French, as you probably noticed, and it actually means peat digger. So it's there's an area in France, the Jura Mountain, where they used to have a lot of peat. Digging that up was a profession that had long sticks. And anyway, I'm not going to talk about that for the next 15 minutes. I'm here to talk about energy. And I have the pleasure, thank you, James, where's James, of talking or giving the talk right after lunch. What I'm hoping to do is wake you up again and make sure that we all understand why everything we're hearing today and in the next 2 days, why actually does it matter? We're going way into the weeds of what we can do with quantum in the space of energy. And what I'm talking about, by the way, is not quantum. What I'm talking about is the macro energy field or the energy area and the challenge that we see. And for those of you that are not from Australia, my apologies, I'm going to do this with the Australian lens, but a lot of it is applicable to the rest of the world. So a few things about CSIRO. I don't think we've had a speech about who CSIRO is. Most of my friends from Australia hopefully know. We're the National Science Agency. And we have more than 6,000 researchers in our organization across 51 locations in Australia. So we're a pretty large team. And we have 9 research business units. And I lead one of them. Marcus Zipper is here, who is leading the manufacturing business unit. I lead energy, but we also have mineral resources, Data 61, our digital business unit, the environment business unit. We have health and biosecurity. We have agriculture and food. So there are a few others as well. And what we set out to do is help Australia solve some of the key challenges that we have. And energy, as you can probably read every day in the press, is one of the key challenges that we have. So for Australia, Kathy this morning basically already took my thunder away. And I think her words were, it's big, the challenge we have, and it's urgent. And I can only re-emphasize that. It is big and it is urgent. And I have a few more numbers than what she provided, so to give you a bit of detail on what I actually mean by that. But why does it matter? Well, let's have a look at Australia. And I have the tendency to wander, so I don't like to stay at the microphone. Can you guys see me in the back? Thumbs up? All right, cool. So what you see here is on the left-hand side is over the last 25 years, the change of the mix in electricity that we've seen in Australia. And that's actually a very good story because we're moving, oops, this was the wrong one. We're moving away from predominantly fossil fuels in electricity to more and more renewables. And I think the latest number we have is 35% renewables just last year in Australia. And that's mainly solar and wind, and a few others as well, but mainly solar and wind. So that's a good story. And that trajectory, if you draw it to 2050, you'll see that the majority of our electricity will be from renewable sources. So, thank you. So, this is on. Yeah, okay. So that is a very, very promising story. What is actually not so promising is when you look at the right-hand side. If you, in energy, in Australia, if you have never looked at this chart, I urge you to go and look at it. I look at this chart every single day, and I'm not kidding you. What it shows you is on the left-hand side, the primary source of energy that Australia has, and this was for 2021. And then on the right-hand side, it shows where that energy goes. So when you look at this chart on the right-hand side, you see that Australia has roughly 16,000 petajoule of energy that was used. Most of it was exported. And here in Australia, we're using about 4,000 petajoule domestically every single year in energy. Now, remember the great electricity story? How much of that is actually electricity? And that's this little number down here. So only 20% of Australia's energy is electric today. So when you multiply those two numbers, that means between 6 and 7% of our energy that we use domestically is actually from renewable sources. And that's the big challenge that Kathy was talking about this morning. And the same you can translate for the rest of the world. I think she mentioned 83% of all the world's energy is from fossil fuels, and that has to be pushed. So why am I telling you all this? So we need to find ways to go and push this electricity number as high as we possibly can. Electrification is the name of the game. And at the same time, we need to stop producing electricity from fossil fuels and have more of it from renewable energy. And that number, by the way, I calculated in terawatt hours from renewable is 73 terawatt hours. That was in 2021, whereas the total energy consumption in Australia in that same year was 1,145 terawatt hours. Scared yet? Okay, cool. I don't mean to scare you, because for the people in this room, this is an opportunity. Because we need to take the opportunity that we have and help Australia go there. So what is the opportunity in Australia? I'm sure you've seen this before, solar. When you look at red is good, meaning a lot of solar. Green or blue is actually very little solar. So this is the country that I'm from, right there, very green, and actually does look like green as well, but it doesn't have a lot of solar. Look at Australia, and we actually have a lot of solar irradiation. I just looked it up this morning. Do you actually know how much solar irradiation Australia gets every year? Anybody know? 58 million petajoule. Remember the petajoule I showed earlier? 58 million petajoule is the amount of solar irradiation that Australia gets every year. That's 10,000 times the energy that Australia needs. It's also 100 times the energy the world is consuming today. So that's a good story. We have a lot of energy. We just need to find a way to utilize it better. Similar story for wind. This wind map shows blue again is low wind, low wind, and red means a lot of wind. So Australia, right here, you can see most of the wind is actually around Australia on the near shore area on the ocean, but also a lot of it is in the west, where you don't see that much in the east. I'll get to that in a minute. And then another opportunity for Australia is we need a lot of new minerals, a lot of material for this transition to happen. And as my 15-year-old son will tell you, if it's on the periodic table, we have it. So everything that we actually need in Australia is right here, and we need to use that. But what will it take to convert all these minerals into energy? It will take more energy. So that means we'll actually have to produce more energy to make use of this. So one thing that I do want to show you is comparing the solar map right here. A lot of solar in the northwest of Australia. Not so much Melbourne. It's actually good today. I don't know if you've been outside, but typically here in Melbourne, we have clouds and rain like the last few days. The same is true for most of the East Coast. Now, when you look, compared to that, I pulled this out a couple of weeks ago, that's the energy usage. So remember, not electricity, but all total energy usage by state. And when you look at the number, where the numbers are high, it's actually right here, where the colors are green. So yes, we can produce a lot of energy, and we can produce a lot of electricity, I should say. And the problem, though, is that most of what we can produce is not in the area we actually need it. So that's another thing, another challenge to keep in mind. And somebody mentioned earlier, by the way, energy generation. I just wanted to set the record straight. We cannot generate energy. It has to be converted from one form to another. But I think that's a big challenge that we can attack. So what is the opportunity for us? What I'm going to do is I'm going to give this group a couple of challenges. I am not the expert of quantum, not at all. In fact, most of the presentations I saw today, brilliant, but way over my head. I saw some really good things, which I've started with 3 challenges on this presentation. There's actually a 4th one that I learned this morning. So the first challenge is we need to distribute the energy that we produce. So we need to find better ways to get the energy or electricity from one point to another. And in form of electricity, what are some of the quantum effects that we can use? We could use some quantum effects for superconductivity. There have been many research areas or research topics on solving the problem of superconductivity. I think there's still a ways to go on making this work. My dream is that we can produce the energy anywhere we want and without any loss, bring it somewhere else where we need it. So that would be a dream of mine that we can do. So a couple of works that has been done. This one was new to me. I have not seen that one before. I think that was in Toulouse where they did this, quantum entanglement for power transmission. Now, why this is on a small scale, I think what we need to find ways to scale this up and make it into a macro. So transmitting and distributing energy from where we capture it into another space where we need it is one of the key challenges. And we have a lot of talks here in the next 3 days to look at that. Second challenge, and we heard a bit about it today, we hear more about it later in the afternoon, and also the next couple of days, is we need to store it. We all hear this, wind and solar are intermittent. That is correct. The sun does not shine at my house at night. But we need to store energy. Remember, we have 10,000 times the amount of energy that we need from solar. So we do need to store some of that. And current storing technologies, batteries in a car, by the way, have typically 250 watt-hours per kilogram. I saw some new ones recently. They get close to 400. But we can push that needle only so far. So we need more. We need a lot more than that. And that's where you look at things like quantum batteries. Quantum batteries have the potential of having much larger energy density, but also charging and discharging much faster. Anybody own an electric car in the room? Just show of hands. Ouch. I have two, by the way. And electric cars, the biggest problem that I have with my electric car is it takes an entire night at home to charge the distance I drive in about an hour or two. So we need to improve the way we can charge batteries and the time we can charge batteries. So that is the challenge number 2 I give to this room. There are quantum effects that I'm aware of, remember I'm not the expert, where we can improve the way we store energy. Now, I particularly say energy now because I heard quite a few interesting talks today. Energy storage doesn't need to be electrochemical. It can also be in many different forms, like bioforms, like optical storage. So there are many other ways to store energy. And I think we've only started scratching the surface. So we need to do a lot more here to help us with storing energy. And this is in particular, for me, important, fast charge and discharge rate. Challenge number 3. And this is where quantum computing comes in. When you look at the current energy system, it's predominantly what you see on the left here. So we produce electricity or we produce heat, and when we transfer it either in forms of fuels or in terms of electricity or in terms of gases through a large pipeline system. And then it's being used in the industry or in a car or at home. The energy system of the future will be a lot more interconnected, and that a lot is a small word, but it's a big challenge for us that we see. Can you imagine we're moving from a couple of hundred electricity generators to tens or hundreds of millions of them that are actually going to be sitting around the continent, and they're going to produce that electricity that needs to be transmitted, and we need to control that. So you cannot just let it go free and then see what happens, because as we saw in South Australia, that fails. So you need to have a way to plan that system, but then also operate that system. And it's a very complicated, integrated system. We have some work at CSIRO looking at how would such a system actually look like. What I would like to see is also, what is the computing intensity that we need to make this work? And as we heard from Jerry this morning, more computing intensity means what? More energy need. So how do we reduce the energy need that we actually need to operate this system with the computing technology or computing power that we have? So that's challenge number 3. That was my last slide until this morning, and there is a challenge number 4. I used to work in photovoltaics. In fact, in 1982, I had my first test of a PV cell, and I was told back then that will never be a future power generation because it's small scale, and it's not something that you can scale up. Look where we are today. So how wrong were people then? And I think the same is true for quantum devices that we can use. So can we scale that up? But my challenge number 4 is energy conversion. We often have energy in form that we cannot use it. Most of it comes with sunlight to us, and we want to produce it into or change it into electricity. Heat is easy, because you don't have a lot of losses when you produce heat from it. But electricity, mobility, airplane flying, trains going, how do we make sure we have very good technology to convert from one form of energy that we have, and we have a lot of it, into the form where we actually want it and where we need it, without having a lot of losses and also without being too costly? So that's going to be my next challenge that I didn't create a slide for is, can we improve the way or the efficiency and cost of converting energy from one form to another? So that's the challenges I want to give this team. Unfortunately, I cannot be with you all 3 days, but I'll be here for the rest of the day. And I'm quite excited about some of the talks that I've seen on paper and this morning. So I think we're already taking some really big strides going in that direction. I challenge us all to find ways to work together to make sure we can scale that up, and we can scale that quickly, because time is going to run out, and we have to make this work. So again, I don't want to scare you, but I want to get everybody excited about helping us to solve this challenge, not just for Australia, but in this room for Australia particularly. Thank you.
Is there a feasibility analysis of using ultra-high voltage DC lines to transfer energy from a high solar region, say Perth, all the way to Sydney? I think this is partially accomplished already in, for example, China. And second question is, do you drive at night while you're charging the other car?
So I answer the second question last. We usually have one car charging at night, that is correct. And I know that is not coming from my PV system, but usually we have one car charging while we're using the other one. That doesn't always work, so I do use some fast chargers in the neighborhood as well. The first question is the solution for ultra-high voltage DC. For China, as long as you have distances that are really far, 4,000, 5,000 kilometers, it actually makes economic sense. For Australia, there are some HVDC lines, not ultra-high voltage DC, but it doesn't make economic sense if the distance is too short, because the inverters are too expensive. Going from AC to DC and then DC to AC at the gigawatt scale is quite expensive. So for ultra high voltage DC to make economic sense, you have to really, really far distances. So I know in Perth, yeah, that is right. But at the moment, there is no electricity exchange between Perth and between Western Australia and the rest of Australia. In fact, they're even on a different grid. Here in Australia. So there are two separate grids that they're running on. But it is certainly something that needs to be looked at, and we need to get that cost down. And I think that's also for the semiconductors, where quantum technology can help us get semiconductor efficiency and cost down, efficiency up, cost down. And that is something where we can, if we can drive that down, and then combining that with low resistance cables, that's the winner. Thank you. Well, I hope I woke them up. That was the idea.